we are going to explore features and visualize some features, and eventually we'll come to building a predictive model. I will give a quick overview to a new tool that came out. It's called Azure Machine Learning Studio. It's neat. You guys probably should start playing around with that. You'll find it really useful. So the goal today is introduce, for those of you who have not played around with R, we are going to show some graphics capabilities of R. And not just the graphics capabilities, we are also going to show how do you really analyze and slice and dice data and try to understand what should be the thinking behind when you are trying to build a predictive model. And so initially I will be doing only the base graphics, the package that ships with base R. But eventually I will show some of the capabilities of ggplot2 and give some examples there. So as I said, I think the goal of the talk is to give an idea of the higher level thinking process that explains how to visualize the data, how to understand your features. I think based on my own experience, what happens is that most people, once they have the data set and they know certain algorithm, what they will do is just they will take the data set and just give it to the algorithm without really doing their due diligence. What can the algorithm really do? Does all the data need to go in there to the algorithm or not? So I will go through that thinking process and we'll see how it goes. And usually, so this is the agenda today. We're going to start with some sample data sets. Some of you may be familiar, there's Iris and motor cars data set. We will go to Titanic data sets, and when we get there, I will explain what the data set looks like. And then we will do some visualization with ggplot2. And if we have time, I will try to build a predictive model right in front. Otherwise, I have this R code and then the outputs and everything, and then we'll see how it looks like. And so the slide deck is going to be completely reproducible. If you go and take the slides and start copying and pasting code from the slides, it should work. So I have the way I have built this slide deck is that I would write something, take the output, paste the code. So I think it should be working in most cases. And then I will show this neat tool called Azure Machine Learning Studio. Again, it's very useful because the great thing about machine learning as a service is that you don't have to worry about, not everybody has a machine with 32 gig or 64 gig of compute. And then once you have, even if you have one of those machines, what if you want to do another experiment? What if you want to do Poisson regression, ridge regression, and lasso at the same time? How are you going to do it? Because you have only one machine. But when you have a service out there, you can create as many experiments, and then the service will actually take care of giving you the machine. So, and then it's going to be a very brief and short tutorial because we have a lot of slides, and let's see how it goes. So first we will go to the visualization aspect of things. So usually this session is, when I conduct this, it's conducted in very interactively. I will show the code, and then everybody will copy, and then they'll type in their IDE. But given we have only 1.5 hours, I think this is about 3 hours worth of work if I do it interactively, but I have to really skim through it. But it shouldn't really impact your understanding of things. If you go back and if you look at it, it will make sense. And when you go back and if you review it, I think you should be able to connect the dots. Okay, so I think this is done. So there's a saying there, data beats algorithm, and which I tend to agree, right? So if you have more data, even a simple algorithm should work. But there are some caveats there. If you have, depending upon how much data you have, right? So eventually the returns from data, they are going to diminish. And also data quality and variety matters, right? So if you're training a search algorithm, a search ranking algorithm, and the data that's going in, it has a lot of bots. Right? So it has a lot of automated traffic. And if you train your ranking algorithm based on those bots, and they can be scraping your website, your search engine, and they're not even clicking on anything, right? So they're just scraping the pages. Or sometimes it's some SEO company, and then they're clicking and going to next page and next page and next page to see where is their client landing on the ranking, right? So those are not typical. Those are not the typical behaviors, and you don't want to optimize your search engine for those behaviors. So how do you know how to train your algorithm, right? So you have to really worry about the quality of the data, and data quality is a big issue. Wherever there is data, data quality is the biggest issue that you could have. And of course, variety, right? So if you are building a model that should work for multiple markets, and you have only data for US market, does it make sense? It may or may not work, but definitely you want to have all the possible varieties in your data set. And a decent performing learning algorithm is still needed. You cannot just have a very dumb algorithm with no due diligence. So it's still needed. And of course, most importantly, you should be extracting the useful features out of data. If you stick everything into the algorithm, sure, the algorithm will do a decent job, but your algorithm performance is going to be great, right? So perhaps only 10 features are important. You're giving the algorithm 1,000 features. So eventually, many algorithms, they will figure out which ones are important, but it's not the right way to do things. Okay, so we are just jumping right into looking at the visualization, right? So usually when I do visualization, the first thing that I do is I would look at the data set. I would eyeball the data set. Maybe first couple of rows, maybe first 1,000 rows. I would look at the data set and try to understand what is it that the data has. So this is a data set. I forgot to actually copy and paste the first few rows here. So what this is doing is, this data ships with the base R package. If you install R, Iris dataset is going to be there. And if you want to get more details on what this dataset is, you can go to UCI Machine Learning Repository, and it has all the details on this dataset. So what this dataset is, it has certain few columns that describe each of the different parameters about different species of flower. So first parameters is probably sepal length and petal length and sepal width and petal width. So this is the 4 columns, which are the predictors. And the last column is the class. And when I load this data, so the first thing is data iris. It just loads that data into memory. The second command, head of iris, it actually gives you first few rows. And you will see that. I think I didn't paste it here, but in a later example, I will use that. And the third thing, it's okay. And the third command is, usually when you have some numeric predictors, what you would want to do is you would want to see really what are the ranges of values. So if I give you a data set that has some ages and weights of some male and female patients, right? So what you would want to do is you would want to create a box plot and look at both categories. So you can create a box plot that has the whole population, both in male and female, but you should really look at the heights and weights segmented by the gender, because gender is it's a useful segment here, right? So in this case, we are looking at 3 species. So species is the class, and we have 3 species here: Setosa, versicolor, and virginica. And it shows you how the values are varying here. So the first is you can call it the minimum value, right? So this is the minimum value. The top line is the maximum value. I don't want to be precise here. I think it's 1.5 of the interquartile range on the bottom and the top, but I don't want to get there. Let's think of this as as the minimum and the maximum. And the dark line in the middle, it shows the median. So this is the most common, or the right in the middle value. And so you have a first species and second species and third species. And I was able to get this visualization just with this simple command. What I said was, I want to plot the sepal length. I want a box plot of sepal length for all species. And data is iris. I'm telling it the data is iris. And then main actually gives it the title. And then the X label is species, and Y label is sepal length. And it's fairly simple. So what insights, if any, can we draw from this box plot? Any thoughts here? So, yeah. So let me ask you this. So if you, what would be the two kinds that will be difficult to distinguish if you have to distinguish between them based on only the sepal length, right? The last two? The last two, right? Because if you see, this Setosa has the, so this is the minimum, the 25th percentile, the 50th percentile, and 75th percentile, right? So most of the values in Setosa really lie under 5.5, right? So really, if you have any value that's 6, it's most likely not Setosa, right? But if there is a value that's 6 or 6.5, you can actually confuse between the next two, because the length values are pretty close to each other. And this will become more clear. I think if you're looking at it for the first time, I think it will take some kind of training or adaptation. But really, what's happening is that if you're trying to distinguish between these two, any of these classes, it's going to be difficult to distinguish between the last two classes versus if you have to distinguish between the first class and the last class. Because if you look at the Setosa, the maximum value is around 6. And Virginica, the minimum value is around 6. So I think you can really define a really dumb classifier, a rule-based classifier. If length is less than, and if you know that these are the only two classes in your data sets, you can really just say if length is less than 6.0, it's Setosa, otherwise it's Virginica, and it's going to be a good machine learning algorithm in this case. It's just a basic rule-based algorithm. Okay? And we can start getting fancy. If I say notch equals true, it draws these notches there, and the rest of the arguments are the same. And what notch means is that it's giving you, I believe it's 95% confidence around median, and it gives you this confidence that most of the time the median is going to lie in this boundary. So it gives you some additional insight into what is the most likely value of the median there. And this is just something that is nice to know, right? So you can add colors, and in notch equals true, I just added blue, green, and red. It's usually good for visualization purposes. Okay. Okay. So how do you save plots? You can save plots in many different formats listed in the table on the left. And really, the way you save a plot is you start with the first line, PDF. If you want to store that as a PDF, if it's PNG, you do it in a PNG format or JPEG or whatever. And then you draw that plot that you're trying to draw. And then, just like you would close a programming handle after you have read the stream, you would say dev.off, and then it will be saved. Okay? And believe me, it will be. In whatever directory you are in, you can just experiment with this, and it should work. Okay, so we can look at the numeric values in a box plot fashion, right? And what box plot does is it gives you a range of the values. It gives you an idea of what the different values are. But we can also have histograms and density plots. I think histograms is it should be very familiar with everybody, to everybody. So you are getting some buckets there, and if you look at the syntax here, what I'm saying is So this is another data set, so it's called motor cars data set. And what I'm doing is I'm plotting the miles per gallon. So this is this is a bunch of cars that have different mileages, and you have cars ranging from 10 miles per gallon to 30 miles per gallon, and I think even 35 miles per gallon. And you can see that most of the cars are around 15 miles a gallon. I think this is an older data set from good old 90s and 80s, I guess, because I don't think if you draw a histogram of all the mileages of the cars that are currently in the market, I think it should have shifted towards 25-ish, right? So now we have smaller cars and more gas-efficient cars. But what this shows is, I mean, within a single command again, right? So I just use a single command. I said brakes equals 10. I split it into 10 distinct buckets. Color does the color, miles per gallon, and it shows main equals histogram means that I'm plotting a histogram. What this is doing is it's plotting the mileages and their frequencies on. So what is the most common mileage from a given car? Okay. And this is the same one in more in density fashion, right? So it's more of a probability density function. And the same thing, and I think I messed up here. So this is not histogram. I think I will fix this and upload this. So there's another function called PDF. Okay. So this seems to be very fairly complex syntax. I'm not going to go into the syntax. What this is doing is it's plotting. It's comparing multiple density plots, and this is what it looks like, right? So what this did was it plotted the mileages of a 4-cylinder and a 6-cylinder and an 8-cylinder car. So we have these cars with different mileages, and then this is what it looks like. So any insights that you get, let me actually do this. I think I should have included the head here. So this is what the data looks like. If you are interested, right? So this is what can people at the back read it clearly? Okay. So what this is it has a bunch of different types of cars, and the first column is the mileage per gallon, which is most likely, I think this is a regression problem. You have to predict the mileage if I put it that way. So first column is mileage per gallon. The second column is cylinders, number of cylinders. The third one is probably displacement, I guess. For those who know cars, I think probably is it displacement, right? And then horsepower. I don't know what DRAT is, weight of the car, and then so on. There is a bunch of different things. So let's actually form some hypothesis here. What do you guys think? What do you guys really think is going to impact the mileage per gallon? What is going to matter if you have to?
Weight.
The weight of the car. Okay, so that's one candidate. Okay, what else? Number of cylinders, right? What else? Displacement. Okay.
Weight.
So weight. The three candidates are weight, displacement, and number of cylinders. And we will see whether our hypotheses are true or not. So does anybody?
I'd also say the transmission type.
Okay. So I don't know if this data. Yeah, it says gear, so I don't know how old the data is.
Probably removed it from the data set.
Yeah. So yeah, so definitely that will impact too. But right. So but in this case, let's take the weight and number of cylinders and displacement as some of the candidates and see which one has the most impact there. Okay. Okay. Any insights here? Does number of cylinders have any impact based on the distribution here? No. So what this is, the blue density plot tells me that for 8-cylinder cars, the 15 miles per gallon is the most likely the mileage that you will get out of an 8-cylinder car. Then you have a 6-cylinder car, and 20 miles per gallon is the most common mileage that you would get. I'm trying to put it in layman's terms, right? I'm assuming that not everybody knows densities of PDFs, right? Practically. And then for a 4-cylinder car, I think around 23-ish, there's a peak, and there's another peak at 32, right? So do you think this finding is consistent with what we just said or what we just discussed?
Yes.
Sure.
Yes.
Okay, sounds good, right? So we can clearly see over here that it's roughly consistent with what we think it should be, right? But we definitely see that there are 4-cylinder cars that are not so efficient. They are on this side, and there are, I think, some cars that are likely to be 8-cylinder cars, and they are probably on the more efficient side, right? So if you just use the number of cylinders, which two classes are going to be most difficult to classify? I mean, which classes will be confusing? So if you're trying to decide whether it's a 4-cylinder car or 6-cylinder car or an 8-cylinder car, just based on miles per gallon, which two are going to be most confusing?
The 6 and 8.
4 and 6.
No, 6 and 8 is going to be most confusing.
I think 6 is the problem here, right?
Well,
if you try to differentiate between 6 and 4, it's still going to be a problem, and 6 and 8 are going to be a problem again, right? Because 6 is sitting right in the middle. But if you have to do 4 and 8, chances are that not many cars will have 4 cylinders and then still a mileage of 8-cylinder, right? So it's basically it's common sense that we already know based on. We have been driving cars, right? So we know that. But it's good to see all that we know right in front, and then just see if it makes sense to us. Okay. And this is cool, right? And if you go back, this is ugly syntax, right? I mean, this is a lot of work, and when you do it, I think you will realize that there is a bunch of work involved here, right? And I will, so I could have started directly with ggplot2, but you wouldn't have appreciated how nice ggplot2 is if you hadn't seen all of this, right? So I just wanted to go through this before we get to ggplot2. So we'll discuss ggplot very briefly, and then we will not go to grammar structure and strengths and weaknesses of ggplot2 because this is not the intent here. The idea is to just be able to explore features and understand features and see if they make sense to us. Okay, so this is your exercise set for home, and I will still show the outputs. You still have the commands, but really I will just quickly skim through these, and I want all of you to actually go back and then try to run these commands and see if they give you any insights. Because I will be showing many of these things again with ggplot2, so I don't want to do this twice. So this is a scatter plot. So this is car weight on x-axis. So this is how we do it, right? Attach actually loads a data set in a memory in a way that you can refer to the columns, and so it has attached it's an R command. But really, if you look at this, I'm using the command plot, and I'm plotting weight against the mileage. And then main is again, it's used all over R, so you should get used to it by now for giving the main label, X label, and Y label. And this is PCH is the type of dot that I chose for plotting, and PCH equals 16 is something else, and 21 is something else, so you can just look it up. So, how to interpret this plot? I mean, can anybody give me an idea? How do we interpret this?
The more the car is heavier, the more gallons.
As the car weight increases, the mileage per gallon is getting lower. How about this? What's the difference between this and this? So forget about the lines and the straight line and this curve, the plus and triangle and circles.
Well, the same thing.
Basically, I overlaid. So this, we didn't have any visibility into the number of cylinders, right? But a lot of times you would want to know the segments in your data. Think about this. So you ship a product in production, and people are using that in the browser, and things look okay. But suddenly you realize, you look at the segments. You have a Chrome segment, a Safari segment, an IE segment, or some other miscellaneous browser segment. It is entirely possible that the behavior in one of the browsers is different, right? I'm just giving an example because so segmentation is it's extremely important when you're doing data analysis. Don't really accept whatever you have, right? So if you think you have some numbers that you have, try to slice and dice them into data sets. If it's population, try it into different young and old or gender-based segments or geography-based segments. So try to use demographics or income. So there can be so many things. And it's the same idea, right? So over here, we didn't have any visibility into the different number of cylinders. And in this case, what this a valuable insight that we have here is that it turns out that this so there are some 6-cylinder cars that have so this is 8, right? So there are some 6-cylinder cars that have an efficiency as bad as a 8-cylinder car, right? So this is actually giving us more insight. It's not just any random points. We know what category each point belongs to. Does it make sense to everybody? Okay. So I will discuss this again when we in the next plot. But what this is really doing is sometimes you would really want to see a big a bird's eye view, an overview of how each variable is changing against every other variable, right? So in this case, so this is what we saw just now. And this plot tends to be confusing the first time when people see it. But if you look at this here, right? So what this means is that if I look at this plot, this is for weight versus DRAT. So I will go to the intersection here. And really, so this is weight and this is DRAT. So any idea if weight is increasing, what's happening to this variable called DRAT? Is it increasing or decreasing? What kind of correlation is this?
Decreasing.
It's decreasing, right? So we can clearly see that there is a pattern here that this is going down as the weight increases, right? But what about displacement here? Can you see that? So this is weight and that axis is displacement. What's the relationship there? It's the opposite, right? So when weight is increasing, the displacement is increasing. And I don't know anything about cars. I mean, I don't know. I mean, if this should be the case or not. But the data suggests that this is the case. If I go all the way up, now this one is weight, and then this one is mileage per gallon, right? So we all have seen this, that as the weight is increasing, the mileage per gallon is decreasing. And so you'll have to probably look at it a couple of times before you can actually absorb it. Okay, so if I look at this plot, does it give me any information about how many cylinders a car has? No, right? And it can be valuable information, perhaps. Overall, it seems like the trend. But if you consider individual segments, the trend may be reversed. And it's not the case in this data set, but it's entirely possible. Let's look at this. Again, this is a package called Lattice. It's another popular package. And I'm using this here, right? Okay, so let's pick something here. So this is for the iris data. And let me actually show you guys iris data so it starts making sense. Okay, so this is what iris data set looks like. So you have the first predictor, sepal length. The second predictor is sepal width. The third predictor is petal length and petal width after that. And then last column is the class, the category of flowers. And there is only 3 unique categories in this data set. Okay? And
We see only one species.
sure, I can actually.
Just a head, right?
Yeah, so this is just the head, right? So I can, if you go and look at it, it's definitely more than that. I think it's not a big data set, so I can probably, let me, okay. So you have pretty much, I think they're in sequence, that's why, okay. So this is the case. Now, if you look at, let's take for example this one. So any volunteers tell me what kind of correlation this is describing here? So we will go all the way here, which is the sepal length, and we go all the way up and petal length, right? So this is telling me there's it's a I'm visualizing the correlation between the sepal length and petal length, right? So if I had looked, assume, I mean, just try to think in that way that there is no color here, right? In that case, this whole blob seems to be going in this direction, right? But when I go to the segments, does it give me any information there?
Yes.
And so what is the information that I get, right? There is a different kind of correlation here versus this blob, right? And I wouldn't have known if I didn't segment the data. I would never have known this. And that's why this is important. Any other interesting things? I think if we look at sepal width and petal length, this one, right here. If I didn't look at the colors here, what would be my conclusion? No correlation, right? It's the blob is spread all over, right? If the x-axis changes, y is spread all over. But again, if I separate setosa and versicolor and virginica, I see a strong correlation here, like this. If sepal width if petal length is increasing, the sepal width is also increasing, right? So you can see that as soon as I segment the data, as soon as I slice and dice the data, the correlation and any other insights, they become much more obvious there. And again, I can, if you guys want, I can actually copy and paste this code, but this is not going to be very productive here, right? So the code is there, and I think you guys can practice that. But I promise, I think I will, when I go later on, I will copy and paste some of the code. Just okay. So this are some other examples. You can have scatter plots with the trend lines and regression lines, and so this is a very rich plot in the sense that you can, in the same plot, you're looking at the densities along the main diagonal, how the distribution is changing for mileage per gallon, and you have the regression lines and the fits there. You have each number of cylinders, they are separated. So it's a very rich plot, and again, I think we cannot really spend time on this, but this is giving you a lot of insight. So we are doing all of this to get to the point when we are able to actually analyze our goal is to actually get to Titanic data set, and that's why I'm rushing to this. So I will slow down a bit when we get to Titanic, so it will make more sense to you. Okay? And this is 3D scatter plots. Again, the code is there. You can see. I don't see any use for that, but you can look at it if you want a correlation of 3 variables there. And then this is another one with a regression plane. Okay. Okay. So we are there finally, 640. Okay. So now, so we will slow down here a bit. So this data set is available. I think you can get that on Kaggle, and it's freely available. You can download it from different places. So this data, where I downloaded it from, it was a CSV file, and it was in this this location. All I did was I said Titanic3.csv, and I was able to actually load that data into something that's called a data frame. So you can look at a data frame as a container. It's a variable. It's an array. For those of you who don't know R, so I think that's how I can describe it. You can. I think the closest example for this is it's just like a database table. So you can refer things by column, by rows, and so on. And then if your data is tab delimited, you do read.table, and you can also specify if it's delimited by some other characters. Okay, so can everybody read that from? Because now we are talking about really what we wanted to do. We wanted to analyze this data set. So people at the back, can you see this data? Can you hear me? Okay. So we have this data set. I'm increasing the font of it. So now now that we are in the problem that we wanted to solve, let's try to build some hypotheses here, right? So based on, we don't know who survived. So the problem statement here is, we want to know who survived. So we have some information about all the passengers that were on board, and some survived and some didn't, right? So first of all, we will look at the data, we will eyeball it, and then see what is it that we have available. We have the passenger ID, we have a flag that tells us whether they survived or not. 0 means they didn't, and 1 means they did survive. And then we have this P class, and P class is the passenger class. What was their class in the ship? And then their name, and their gender, the age, sibling and spouses, whether they had any sibling or spouses on board or not, and how many were they. So, and I think this variable has values up to 8 or 7. So there were big families on board as well. And then parents and children, and then the ticket number, the fare, the cabin they were in, and this is the port of embarkation. And I think one was Queensburg, and there was some other Southampton, and third one I don't remember. So this is the code for all of them. Okay, so I want everybody to actually be more proactive here. What would be some of the hypotheses? Who was going to survive here? Yes, one. Okay, so first hypothesis is the people in the class 1, they would survive. And we are assuming that class 1 means the first class, right? So, okay. But that's, so usually I think this is true in this case, right? But I would caution against that, because when we go to the data, usually what happens is that the person who's generating the data is not the person who's analyzing the data. So don't assume things, okay? Because the person may think that, okay, this is the class 1 in the sense, this is the, not in the better sense, right? In the order, I mean, maybe this is the first class that I thought of, hence this is class 1, right? So it could be, first class could be different meanings. So I think it's very obvious in this case, but these kind of confusions happen when the person generating the data and the person consuming the data is not the same. Okay, so class, what else? Women, sure. What else? Age, yes, so women and children, right? What else?
Location and cabin.
I'm sorry, what was that?
Location of the cabin.
Location of the cabin, and we don't know that, right? So, but the cabin, if we put it that way, the cabin would have an impact there, right? So cabin may have an influence. How about, so we talked about the gender, the age. How about siblings and spouses? Spouse. Any idea? Would it, so if you have more people with you from your family, are you less likely to survive or more likely to survive?
Less likely to survive.
Yeah, so for most decent people, I think you're less likely to survive, right? I think, and it's not a really, not judging someone, but I think it's usually the common sense is that most people, they wouldn't leave their family behind, right? But there are cases, right? So probably men may be left behind and their family goes. So right, I mean, so they probably that can be a predictor there, right? How about parents and children? So if a person has a child or a parent there, are they likely to, like, is it going to be impact their ability to survive? A possibility, a chance to survive?
Maybe.
Sure, there's a possibility, right? And we won't be able to do all of them. I will just show some visualization there. How about ticket number?
No.
Okay, let me go back actually. How about the passenger ID?
Who assigns the passenger?
So one question is, who assigns a passenger ID? Does it really matter?
It just matters if they're unique for each person.
Okay. So in this case, I think passenger ID, it's just a number, right? It's just there. But really, I mean, think about this. Let's say passenger ID is correlated with the cabin. So people, in some scenario, the people who came first, they landed in the lower deck versus the upper deck, right? So there can be so many things. But in general, I think the identifiers, the GUIDs and IDs, they usually are student IDs. These are not useful predictors, but you have to be watchful and careful about this. You have to be really cognizant of the fact that you can make a mistake and then just lose some information there. How about the name? I'll come back to ticket. Could name be a predictor? And I want a show of hands. I think just to maybe see more energy there, right? So, how many of you think name could have an impact on survival? Very few people. And is it fair to assume that people who are not raising their hand think that? Okay. Yeah. You have a question?
Could be associated with the class of the passengers.
Yes.
So, and the level of wealth. So, a lot of the lower class passengers think being certain, to work on other ships, so that could be correlated with the
Sure. So name can actually depend. So let's say you didn't have a gender column there for whatever reasons, right? If you didn't have a gender column, you would actually derive the gender from name. There's a possibility, right? So you will see what gender it was. And what if the name has sir or general or something, right? So you never know, right? So name actually can have some clues into whether it's the person survived or not. I'm not saying it's the case here, but just to give you a general, you have to really think like a detective here, right? So just keep thinking that what is it that you can use here. Okay, coming to ticket number. Based on the discussion, any thoughts?
Why did you pass on sex? Because I remember on the show that they said women and children go first.
I'm sorry, what was the question?
Why did you pass up the gender of the person? Because back then, or usually they say women and children.
I did pass that. So I think that was the first thing that you talked about, right? So gender will have an impact, right? So definitely gender will have an impact. And even now, I think it should be the case. So somebody actually in my last presentation, somebody said that I think it's not the case anymore. But as it turns out, so now if any incidents like this happen, it's not women and children who survive, most of them, which is sorry and unfortunate, but this is how it is, right? But in this case, Titanic is known to be a case in which it was more women and children who survived than men. Okay, so ticket number.
So tickets would hint about some segments of the sheet which probably falls over the boards.
Ticket may have some indication whether it may represent, I mean, it's a first class ticket or some certain cabin or some privileged person, right? So,
plays because boards are placed. I don't know if they're
sure, I mean, it can really indicate the topology, I mean, how things were distributed in the cabin. So ticket may have some clues, but really you will have to explore the features. Maybe A has some meaning, A/5 PC, or maybe only some subset of the tickets. Yeah.
Yeah, so the best analogy for ticket number is sort of like seating on a plane. We have A, B, C, D, E, F. Person who's most likely to smell it, certain situation, is probably next to the window.
Sure, I mean that's the case, but I mean if you didn't crash right in the midair, right? So I mean if you had the opportunity to land on water, only on water, right? Of course, right? But if you just went all the way to the Earth, I don't think it makes any difference. But yeah. But that's a good point, though.
But in this case, if you're using ticket as a proxy for their class,
yes, I mean
then what you really want to look at is class and not ticket.
So these are correlative variables, right? So you have to make sure that you don't use two correlative variables because it will give you this false sense of accuracy, right? So, and then that is the kind of analysis that you would do. You would not want to use two variables at the same time that are correlated. Okay? And similarly, fare may be correlated with the ticket and the cabin and the class, right? So there can be some variables that are correlated there. Okay? And fare, I think, possibly fare higher, people who paid higher fare, maybe they survived. And then the cabin. Yeah.
The cabin here, we're missing some data.
Actually, so it's only cabin which is where it is obvious, but there is some other data. I think some ages are missing, some genders are missing, and then so there are some missing values. So this is it's a relatively easy data set, but it's really good enough to actually get started. It's not like iris data set, which is very well behaved, and then you just plot whatever you want to plot. So, but that's a good point, right? So you also have to look at the missing values here, right? So, those are there. For the cabin, yeah.
Question. So about correlated data, so we run some sort of analysis to figure out.
Yes, you have to. You have to.
Cover that later, or?
I won't be able to do it. I mean, so it's so whatever if I get into that direction, it will take a lot more time. But I think you are going to be, by the end of the presentation, you are going to be armed with all the tools that are needed there, right? So you can go home and then try. I mean, not all the code is going to be there, but you can really, when you go home, you will be able to reproduce some of the things and actually add in, experiment a few other things.
But just like a quick thing, so it's just variables you have like your own correlation function, it's like one, let's say it's more or less all good.
Yeah, so one is a very strong correlation, like it's like the same, right? But you wouldn't see that strong correlation. But if it's strong enough, then you would actually worry about that. Okay. Okay. So for cabin, I think perhaps CN85 and CN123, or possibly B and D and other things. So they may not make any sense. But what if you bucketize them into A, B, and C, and D, right? Then you can extract features out of that, and that's a good practice. I mean, you should always be looking at how to extract more features. For instance, age. So you may not see age to be a good predictor, but what if you threshold that in whatever the legal definition of a child was at that time, and then you create another feature. You say anybody who's less than this, I will mark that. I will add one more column to that row, and then I will mark that person as a child. Otherwise, it's an adult, right? And then suddenly you have another feature which may have been lost in the age itself, right? So you have all the ages. It may not be obvious completely, but as soon as you split that into adult and child, it may become obvious.
So are you talking about extracting and then prioritizing the attributes that
Yes. You sometimes you have the data that you need, but it's not in the form that you should have it. So you really need to actually you need to modify it a bit. You want to extract features out of that. Okay, and it comes from really it comes from intuition. When you start solving problems again and again, then you realize, okay, I think it's not that difficult at all. Yeah.
This is a case of given if there are a lot of missing values, so what we should do, we should drop that column.
There are different techniques, right? So you can, if it's a continuous value, you can replace it with median, mean. You can whatever, if it's a classification problem, the average of that class, you can completely get rid of the rows. It totally depends on your situation. If you have, if you start removing the rows with missing values and you end up with 10% or 5% data, you wouldn't want to do that, right? So you would, it is really how you, what is your situation and what is your unique situation. There's no single answer to that.
Could you please repeat the question?
Okay, so the question is, if you have missing values, what would you do? Do you remove the rows or you do something else? So the answer is, it depends. If in many cases you may be able to replace the missing values with the median value or the mean value or the mean value within that particular class, or you may want to remove the row, right? So there can be many different techniques. You wouldn't want to remove the rows if there are a lot of missing values here and there, right? So you don't want to end up with no data at all, right? So because but what if the column is a good predictor, right? So there are values that are missing, but with whatever values there are, it's a useful column.
Or we may assign values depending on other column,
sure, and certainly, I mean, there are many things that can be done there, and so handling missing values would be actually a detailed discussion in itself. Yeah.
What do you do when number of parameters are so many that you don't know?
You do feature. Yeah, that's a good question, right? So, and this is usually the case, right? So think about Amazon or Google or LinkedIn. When they are suggesting you products or recommending your friends or doing any recommending connections to you, it's not a 10, 12, 30, 40 features problem. They go to the finest level of granularity that they can get data on, right? So did you come back in last 6 hours or last 10 hours or last 24 hours, last week? Did you, are you a holiday shopper or not? What's your zip code? What's your address? Which city are you from? So can you imagine, I mean, so those companies, just take Amazon for example, they literally would have thousands and thousands of features from where they will have to extract the most useful features to build their model. Who should they send out a Prime offer? Who should they send out a Kindle offer, right? So who should read this book and not that book? So all of this actually requires lots and lots of features, and that's why really, I mean, doing predictive modeling is not, it's no big deal, but doing it on scale, that is where things become more interesting and more challenging. And that's that is the problem precisely that these companies have solved, and then they are really making money out of that. Okay, and the last one is the port of embarkation. So I think there are 3 distinct values there. Okay, so what is the data type of each column? So I'm showing this because I think this can be a big pain point when you go back home and try to do it, because it turns out, so lapply Titanic class, it just gives me the class of each column. So passenger ID is an integer, I'm fine with it, but survived is also an integer. Do we really think it's an integer? It was 0 and 1. It's really a label. I mean, we shouldn't call that an integer. But R tries to infer based on whatever data was given to R, and it thinks it's an integer. But when we are doing a classification problem, we have to explicitly cast the target variable into a, if it's a numeric variable or integer variable, we have to convert it to a categorical variable just to make sure that the classification algorithm doesn't get confused. So it turns out, and then there are others as well. So when you get this, do this, you will see all the examples, all of these labels here. And simply, you can simply cast each of the this particular target variable just by saying as.factor, and then it just converts that to a factor. Okay? Okay. Any thoughts here? Do we think our hypothesis was correct? Here, no. So we didn't get there, right? So right now it shows what was the proportion of people who died versus survived. So more than 50% people died, but it just shows some proportion, right? So how about we add some more color and more some numbers and percentages to it, right? So this is all the code that you will use, but this gives you an overview really. What's the proportion of people who survived and versus the people who died? Okay, so this is just to get accustomed to the data set. Okay, and this is just another fancy, so this is a package called By3D. So if you are presenting your data and your findings, it's always a good idea to visualize your data nicely. Okay, so let's come to this. We talked about this. We think that gender is a good predictor, and this is all the this is some code that will create a pie chart of gender and whether they survive or not, right? So, and again, you can replicate this using the code that I mentioned. Okay, was our hypothesis correct? So almost more than 3/4 of men actually died, and more than around 3/4 of the women, they survived, right? And this includes children, like female and male, let's call it that way. Okay, so now if I had only one feature here, if I build a model that just says if it's a male, I mean, I know for sure it died, right? So it can be a very simple classifier. If gender equals male, class equals died, else survived, right? So this is my machine learning algorithm here, right? Just based on this insight. And it's going to be fairly accurate. And how many of you have ever played with Kaggle at all? Okay, only some of you. Okay, so I didn't realize that. I would have, otherwise I would have shown you. I mean, it's very easy to create an account, and then you can just create a model based on gender, and then upload your predictions, and you can see that it's fairly accurate, just based on gender. It should work. Yeah.
What did the people who didn't have a gender, what was their?
Yeah. So it turns out that there was a case, right? So there, because there are some missing values, so we don't know why those values are missing, right?
Yeah, did they show any kind of sort of pattern?
No, so this is explicitly only for the gender that was identified clearly.
Yeah, so they didn't show a pattern.
I didn't actually look into that, so that's a good homework for you then. It's just, I mean, what you will do is you will just replace this with appropriate filters, like gender is not equal to male and not equal to female, so you will have, or I think it's you can simply look for a missing value, and that should also give them all, because there are some missing values there. Okay.
Okay. Thanks.
Yeah, but that's a very good point. I mean, we should actually look at that as well. So this was a good enough predictor there. How about age? We agreed that age would be a predictor, right? So I'm using this summary of age. Summary is it's a function in R which gives you I think this is a 7-point summary here. So it gives you the minimum age, and so they have ages in this. I think they have somehow normalized the age in this fashion. and you have the first quartile. So first quartile is about 25% of your data. So 25% of the people were under the ages of 20. The median age, like right in the middle, was 28. The average age, the mean age was 29. And then third quartile is 75%. So 75% of these people were below 38, and there was someone who was 80 years old as well, right? And then there is the missing values are 177. Okay? And we go to okay. So what if we segment the age by survival, right? So we want to look at the summary of ages only for the people who survived and only for the people who didn't survive, right? So I'm trying to segment this and see is there any difference in age in the distribution when it comes to whether they survived or not, right? And I'm going to be using box plots that you have seen, right? So on the left, so we have, so this is actually the age distribution. I think I should have, let me actually show you on my screen here. I think I, again, didn't copy and paste this summary statistics here. Let me do that. Okay, so this is the people who did not survive. And then if I just change this to 1. Any insights? Or I think an understanding that there is no insight here is an insight itself, right? So
the oldest person survived.
And
the youngest person.
What is that?
The oldest and the youngest person survived.
Okay, oldest and the youngest person actually survived. Yeah, that's a good insight, right? So can everybody follow this, right? So one insight that I didn't notice that, by the way.
Because I know the oldest.
Yeah, I know. But yeah, that's a very good observation here, right? So the one observation here is the people who were the person who was the youngest on the ship and the person who was oldest on the ship, both of them survived because the min and max are there, and the min and max for the people who died is greater than that, right? So that's a good observation. What else?
The median is the same.
Any other insights? Just even if it's wrong, I mean, just think aloud.
No correlation.
No correlation. Okay. So because the median age in both cases is about 28, the mean age is they are close. I mean, yeah. So the people who were slightly older, they died, but
the median wouldn't change, would it?
But it's the median of that particular group, right? It may or may not change, right? So I agree, right? But it's the median of that particular group, so it may change. And we have the third quartile in the died. Yeah, I mean, slightly older people there, but really, I mean, there's not much here. It doesn't tell us anything. But we had this hypothesis. We said that age has an impact on survival rate. So what's going on here?
We do see that younger is like the second survival is a little bit younger as well the second, right? It's like 19 versus 21 and 28.
Okay. So any more specific? Yeah.
What about the combination of factors like age and class?
Yeah, that's entirely possible. But we just we discussed this. Our hypothesis was that age will have an impact, right? But over here we see that there's not a very strong impact here. Also, that's a valid point. There is a lot of missing information. Okay. What else? Yeah.
I think it could be possible that you have more young child and more old people survive, but you don't see it on this.
Exactly. So what should we do here?
Look at
Okay. So do you think if we because when we say age age will have an impact, we're not talking about any age. We're talking about children here, right? So gender was there, but when we talk about age, it's not just any age. But when you're looking at this, it's an aggregates, right? So we have to find a way to actually separate children and adults, right? And then we may want to create another column or another category that actually sets this threshold. If age is less than this, then it's a child versus it's an adult. Okay. Okay, so we looked at that, and these are again some box plots. The left one, I'm leaving that for you to just think about this for your homework. But this is the age distribution by gender. Let me zoom in case it's not visible. So this is the age distribution by gender, right? So on average, men were, the median age for men was slightly higher than women. And the circles on the top, they are outliers. So there were some very old men as opposed to women. So women were relatively younger, but men, there were some very old men who were on board. And this is, those bubbles actually signify outliers there. And then we have age distribution by survival, and it looks like the median age for surviving people was lower, but I will let you guys actually do this as a homework because we still have a bunch of things. Again, try to build a histogram, try to look at the density there, and so this is all that you can do at home. There's some interesting insight here. So, okay. So we have this kernel density plot. So this is the distribution of ages by survival. So the red one is the distribution of people who died versus the green one, the age distribution of people who survived. Any insights here? Do the two look different? Okay, yeah.
How did you get people with negative ages?
So this is a PDF, right? So it's a smoothing function that would take you to the less than 0, right? So that's a very good point and good observation. I'm happy that you were paying attention. But really, what happens is that when you're fitting a density function, you can have a lower value as well. So it just signifies that that smoothing that happens on the left. Okay. What? Sorry. What was that?
When you're estimating densities, you can impose the restrictions so that the values can't be lower than 0, right?
So yeah, it is a density and it can be less than 0. So there can be values that are less than 0, right?
Somebody is taking extra care to save children.
Just a minute. I can?
When estimating the density, can you impose the restriction that you can't have values less than 0?
Why would you want to do that? Because I mean, it's so you are actually impacting the way the smoothing is going to happen, right? So you're going to shift this key piece of information to the right, right? So this is somewhere over here, right? Does it tell you anything? There's a bump there. What this shows is that this age is stage is high probability age, and suddenly there's a blip, and then it goes.
So they save the kids.
These are kids, most likely very little kids, right? I don't know what age, but the data is right there, right? And again, we can always slice and dice it.
Your bump might be an artifact of the smoothing function.
It can be an artifact, but that bump is there, right? So bump clearly shows that there was. Yeah, so that is an artifact, right? So and we agree, right? So the negative value is the artifact, but that bump is there based on data. And we don't want to mess with the smoothing function because we will shift this. Okay? So this actually is some evidence there that age had something to do with survival. Okay? Does it make sense? You have to keep going. So this is code for data splitting, and I'm not going to go through this again. But whenever you are a novice mistake when you are doing predictive modeling is when you train the data on the data set and you test on the same data set. So it is going to work, right? But it's a good practice to randomly partition your data into different partitions, and you test on, you train on one partition and test on another partition. Otherwise, if you are, it's just like you're making your algorithm memorize, and until it just memorizes your data completely, you're just going to keep on training, right? So this is the code for partitioning your data, and you can take a look there. Okay, so I'm going to just try to just be very quick. We have a lot of material that is left. So now, so this is ggplot2. This is a very nice graphical package. And the data set that I'm going to use here first is to introduce the basic things, and then I will come back to titanium. So this is diamonds data set, and so this is the carats and the cut. And cut has, I think, 5 values: the color, the clarity, depth, table. I don't know what table is. I don't know what depth is, but some of the other things probably have some idea. X, Y, and Z. No idea what this is. These are some numbers to me, right? So what would have an impact on the price, for instance, right? If you are trying to predict the price of of a diamond. Okay. So does the histogram look any different? In terms of like the way the histogram looks. So this time I used, instead of the base histogram function, I'm using the ggplot histogram function. And the way ggplot is if, so this is actually, so ggplot actually renders things in layers. So this is the first layer. What I'm saying, what I'm telling my function is that I'm going to plot this data set, and the next layer is saying that I want to build a histogram, and it's visibly better than what we drew, right? I mean, our histograms, they didn't look that nice. Similarly, if I go to the density function, so this is the first layer here. I'm again saying that this is the plot for this data set, and then this is the second layer, which is telling it that okay, on x-axis plot the carats. The values are going from 0 to 5, and then fill it with gray color, right? And it's once you start doing it, I think it should be intuitive. And this is a scatter plot for carats. And if I look at this, so again, this is the first layer here, and first layer is saying that plot ggplot for data set diamonds, and on x-axis plot carats, and on y-axis the price. Any correlation between carats and price, right? So it's obvious, right? So with increasing carats, I think, so the price is roughly on the higher side, but not too strong. But what if I want to know? What if I want to know the correlation by color? You remember there was a color column in there, right? And so this can be misleading here. So this color refers to the column, and this is a parameter that I'm passing. So this is the parameter, and this is the column, right? So there were different colors. We don't know what colors those were, but these are different color values, right? So now we have been able to plot them separately. All of the whatever colors those were, right? So the color D, E, F, G, H, I, J, whatever colors those were, we were able to segment them. Even nicer, right? So what this is, what we are doing, trying to do is that we are plotting all the segments separately, just slicing and dicing the data until we understand something, until we get something out of it. And it's just literally, I mean, just 2 or 3 commands that I'm using, and just installing a package, and then we are done. Okay, can there be more? Yes, even more. So look at this. It's beautiful, right? I mean, so you have carrots and you have price. You have within each category, you have, I think, fair, good, very good, and premium, and ideal was the quality of cut, right? So, and then there was another variable. What was the first one? I think there was some imperfection metrics metric there. So now, I mean, you can if you look at this, if I look at the first row, it's basically if you look at it, it's a 4-dimensional plot really. I mean, you are adding more and more dimensions there, and you're slicing and dicing your data to the greatest detail that you can, right? Okay, and Titanic data again. Okay, so what do we have here? We have, if we look at this here, so what we are doing here is we have y is fair, right? So this is fair, and x is p class. So this is p class and this is p class, and then we are doing a box plot, which is for different ports of embarkation. Is it different? And the first one is actually missing value. If you look at the first one, there's no value here, and this one is Queensburg, I guess, and this is Southampton. Do they look different? Visibly different, right? So we can see that the people who boarded from, so there were few people from Queensburg, and then definitely the people who were at from Southampton, I think it looks like that there's a lot of outliers here, and I don't want to go into the details. I think we are short on time, but it just gives you that idea that how you can slice and dice data when without there. And let's see this one. This is did. So now it is fair and survived, right? And I actually created a column adult and child, and then male and female. So look at this. I mean, how many? So this, if you look at this plot, this is basically whether the person died or survived, only for male and only for children, right? So this comes, it's male, child, survived, died or survived, and then again that is for male, adult, died or survived, and then you can really slice and dice data there. Okay? And there is, just try some variations. I mean, you would be surprised how, I mean, once you start doing these different variations, you will see how insightful and how valuable this is. So basically, all you have to do is that the blue here, so replace any numeric variable there, because we are doing a box plot, and type any categorical variable and then any categorical variables here, and try to play with this, and then you will see how patterns will start emerging there. Okay, let me actually directly skip to really random forest, and I will show you this for just to. I wish I had more time, but this is a lot to be covered. So I'm using the package called random forest. Oh, okay. So it says it could not find a package called random forest. So I'm doing. Okay, so it was on my desktop, I guess. So really, let me, I think in the interest of time, I will
miss the E in forest.
Oh, okay.
That's the bad problem.
Okay. Okay, so I want to make a point here because we had some observation there, so I want to actually make a point before we move on, because this so I can actually, let's go back and print. Okay, so a quick point to note here is you guys remember that, so this is a confusion matrix. So, so what this shows is how many of their setosas were classified as setosas. So it's 50. How many of setosas were classified as versicolor? 0, and virginica. But if you look at how many versicolors were classified as versicolors, it's 47. And there were some of versicolors classified as virginica. And at the same time, 4 of the virginicas were classified as versicolor. And then this is, some of them were classified as wrong class. Does it ring any bell? I mean, did we notice something when we were analyzing features back early in the presentation? We saw some overlap there in the distributions. So definitely these two classes are likely to be confused with each other, right? Okay. What I will do is I will send all of you the slide deck because I really quickly have to show you how you would do this in Azure Machine Learning Studio. And a Titanic example, once you ramp up on this, you can actually try to do it yourself there. So I can quickly, so you can use random forest for regression, for classification, for clustering, for getting the importance of the variables, you can do that. So all of the data is there, and then this one is a neat one. What this shows is that you can actually also get variable importance, how important a variable is in getting the classification. And what this shows you is that, so these are two different criteria for getting the variable importance. And so this shows, the first criteria says the weight is most important, and second one says that the displacement is most important. So it actually turns out that our intuition was correct. And then there is some other data that we have and some resources, okay? So I will quickly jump to this should be open there. So this is a new tool that Microsoft released recently, and it is neat, really. So what you can do is, this tool actually lets you upload your data set. It's machine learning as a service. So you want to do some classification or regression or any other machine learning task. So it has a bunch of different algorithms which are already there, right? So you have, so this is some of the standard data sets that you already have. You can play with these data sets. You have different data formats and versions. You want to convert data to different data formats, you can do that. Data input and output, you can read data, and you can really read data from any web source. You specify the URL and you have the data. It's loaded there. Then you can do different transformations of data, different kinds of filters. And I love this thing, because if you, I did the splitting and partitioning code. I left it there, and the ugly code that there, just to convince you how useful this thing is. Because this thing just neatly, I drag and drop a partition sample here. I will connect my data set to it, and I choose what kind of sampling I got and what kind of what rate of sampling. And then if I, let's say if I choose 0.5, and then I run here, and it is, I don't know where the machine is. It's a high compute instance, and it's running in the cloud somewhere. And it will give me all the things really that I need.
Does it give you the algorithms too, just out of curiosity?
Absolutely, absolutely, and I will get to that. Okay, so this is, and this is this is my data set after partitioning. So I have 446 rows and 12 columns. And before partitioning, I had 891 rows, 50% sampling, right? In 12 columns. And then I'm using a decision two-class random forest. But there is a bunch of other machine learning algorithms. So you have a bunch of machine learning algorithms. There's a long list of machine learning algorithms, and you don't have to do anything. You just maybe be fine-tuning the parameters, and you have clustering algorithms, you have regression algorithms, and I mean, it's really it's a lot of things. And then even if you have a big data set, yeah. What is that? Yes. Yeah. So there is something called the R module. So really what you can do is you can create your own R module, and you can execute R script, and you can create that module, and then you can nicely define the input and output, and then you can create your own module really in R. And I've heard the news that Python is coming next. Is it true?
So I think very soon we'll be releasing a SDK which will let you basically use the .NET framework to code up your own modules. So an SDK will come out soon.
Yeah, it is. So you pay by use. Right now, I think they have a promotion, $125 credit per month. I don't know, but I'm using it for free. I don't use it a lot, in the sense that the free tier is enough for me to actually just do all the functions that I do. So I wish there was more time. I mean, this is neat.
Question: how do you publish? So you did this. How do you publish to the
publish as in
your results, business users to the backend database?
Oh, so you mean how can other people use it?
Well, number one, if it's your final result, how do you present it to the business users? Number two,
okay. So you can dump that. You can download. You can dump the data set. You can save it as a data set. You can save the output. And the neat thing is, you can publish this as a web service within a few clicks, right? So you build a model, and now you can let anybody else out there use that as a web service. So that's the feature is there. And I think I have already scheduled that talk, and probably I will be doing this. This is neat. I mean, it's you can think about this as Apple, the way they disrupted the marketplace for mobile apps. Now this is something that anybody can build their machine learning model and then publish it, and then really make money. I mean, if they are good enough, they can just really publish that and then let people use it. Okay, you go.
How well supported is it with documentation and tutorials? Since it's pretty new?
So documentation is catching up. Right? So I think that is one thing that needs some effort there, but eventually it will catch up. And if you are, if you have a reasonable background in machine learning, it will actually, I think you will be able to use it. So for instance, this is my Titanic dataset, right? So I just uploaded the dataset and saved that, uploaded the CSV file and created the dataset. And look at this. So previously, what we were doing was we were running all of those commands to get all the box plots and histograms, right? So right now there is only two options here. So I can get so histogram for survived doesn't make any sense, but let me actually get the histogram of some other metric like age there. And so let's get, so this is the distribution of age, and I can also get a histogram of age here. So we have, so we get the histogram here, okay? And then you guys can really explore that. Another neat thing about this is, I copied this and paste it here, okay? So this is, I'm creating another experiment here, and when I created this experiment, I want it to be a bit different. I don't want four decision trees, I want 6 decision trees. I just changed this, and so quickly I was able to replicate the experiment with the different parameter. And then what I will do here is I'm going to, so this is going to show me how, and it's a small data set. I think it should just, so it's queued right now, it's gone, and it will check out a machine somewhere in the cloud for me. It's a high compute instance in case I need a bigger data set. I don't know what's the underlying logic. I mean, how do they decide if I really need a high compute instance or not? But so right now check shows that the random two-class decision problems have been initialized. Now the model is training. And did anybody notice in the new run, the left side is already check, right? If I have to run my code again, it would run again no matter what, right? So right now these decisions are saved, the left workflow, it was already saved in the cloud, and it didn't need to run again. And now I have this here, and this is another one. I just trained I trained and evaluated another model. Yeah.
The schema, when you're reading from the databases, from multiple databases, do you have to do rework before, or
you have to specify what's your target column, and I will get to that. That's a good observation, right? So this shows me my rock curve, right? And usually I would be calling another function for doing the rock curve, right? So this is giving me a rock curve. So this is random guess, and this is the scored data set, and this is precision recall, and this is left. So there is all the metrics here. So true positives, false negatives, false positives. So this is the confusion metrics, the accuracy, the precision, the F-score, the recall. I mean, it's just happening within a blink. I can also compare two models here, right? So this one, okay, so I think I can do this, and this will actually compare two models. Which one is better? I can do that, right? And it will plot the rock curves on the same on the same scale, and then it will show me, because I can immediately tell which rock curve is better than the other, and then it's right there. Is anybody waiting outside for us, or because I can actually no?
What are the costs associated with this?
So for me, I think it's if I recall correctly, because I'm in a program called BizProt now, but if I remember even before that, so do you know what's the pricing for this? I think $125 to up to $125 you can get a credit, but I think my limit is higher because my limit might be 200 because of being in their business program. So basically, if you are a startup, you can go and apply, by the way. So any startup would get that into that program. But for individuals, I think it is $125 because I don't work for Microsoft, so I don't know what exactly is the case.
How about students?
So you may have, if your school may have a partnership there with them. So you can really check with your school or figure out. Yeah.
Would you say this is for production machine learning work? I mean, if you had an online real-time collaborative filtering installation, would you use Azure, or is it more for prototyping?
Both. So I can be having my workspace, and then what I can do is once I'm done, I can go ahead and save that workspace as my production workspace, and then expose that as a web service to production. Yep.
And you mentioned that you're going to send the slides. How's that possible? Are you going to post it on the meetup webpage?
So this thing?
Yeah.
So I think this is not going to be posted in slides. This is something I can maybe send the URL. Go sign up for a free account. If you don't use it, you don't pay anything, right? So just go and sign up, right? Unless you kick off a job in this Azure machine.
No, I mean the PowerPoint that shows just now. You said you're going to email us the slides. Do we give you like by business card or something, or what?
No, so I'm not going to email. It's going to be uploaded on the Meetup page.
Uploaded in the Meetup page.
Yeah, and then I will send out an email through Meetup as well.
It's just in the Meetup page, that's all. So that's why I get.
Yeah, because I mean I don't want to spam everybody, right? So I mean, so if you need it, you can download the slides. Otherwise, it's not needed, right? So coming back, your production, right? So you can deploy that as needed. So it's both for your prototyping and all the things, right? So let me know if somebody is waiting outside, because this is actually some fun stuff here. look at the samples, right? So you don't know, right? So you don't need documentation really here if you have these samples. Oh, by the way, let me actually go to
public preview.
yeah, it's a public review. It's not a final product yet. Okay, so we have this workspace here, and I wanted to show this thing. This time I'm comparing two models. So for those who want to leave, I mean, they are welcome to leave. I think we want people to be held up here. Okay, so if you look at this, both models are roughly performing the same, right? The ROC curves are almost overlapping here. And then we have the precision and recall for both of them here, the accuracy, and then a bunch of other metrics that are there. And I was actually going to the samples. So they have a bunch of samples here. So some regression examples, some binary classification examples. Let's just open one of them. So this is a very well-known data set. It's got UCI, again from UCI repository. So they have a missing value scrubber, right? So, and you can choose a custom substitution value then, right? So you can, my browser is not behaving. But so, let's see if I can, what is it? Refresh speed? Oh, okay, I see. Oh, okay, yeah. Just didn't realize. So it should be a copy of it, right? It should happen in there. So I saved this, and now if you look at this, now I can replace with mean, I can replace with median, I can replace with mode, replace and remove entire row. So it's again mean, right? I can do this. I can do a whole bunch of other things here, right? Then I have this project columns. I can split the data. I can initialize the model and train the model, store the model. There is a recommendation, some recommendation engine examples too. Let's go back here. Yeah, movie recommender. So that's there. And you can see that again, I have some movie ratings database, and then again split, a train recommender, score the recommender, and then you can do a whole bunch of things. Really, I mean, it's once it goes out, once they fix the minor pain points here and there, it is going to be something extremely useful for people to get started. I mean, so really, I mean, if you want to get started and you are beginning to actually do some machine learning, it's a very useful tool. Yeah. Okay, so yeah, sorry. I mean, the last time I think what happened was that I tried to go slower in the beginning, and then we had a lot of material remaining. So at least I rushed, but at least I finished. So, but if you are really interested in this slide deck, would help you figure this out. Yeah.
That's my question. I'm grateful that you're making the slides available, but could you also make the slides for your previous presentation available too?
I think I did. Yeah. I think I did. I did upload and send out an email. If there is any of them missing, let me know. I will double check it. And then this is going to be there was going to be a bit of cleanup. And I will do them in the next couple of days. Any other questions about any of the topics? Anything? Yeah. Okay, so thank you.
Thank you.